Right, this is a review of the paper set for the 2025 February PPE Year 13. This is the specimen paper given to us by the IB. This is the closest we've got to a past paper. Specimen papers are never perfect, but they're a pretty good idea of the kind of things you're going to expect. A couple of general points I would make before I go through the paper is, if you're asked a question and you've got lots of choices, for example, a load of organic chemistry molecules, and you're asked about boiling point or something, please draw them out fully. It gives you a better chance of being able to work things out. Don't just kind of try and do it all from sight. Right, this was a full paper. There's a few questions in here, the bits of the course we've only just started doing. Okay. So the first question is on chromatography. You're interested to know about thin layer chromatography in some detail, and just generally how chromatography is used in chemistry for separating mixtures of simple covalent substances. And the way that it works is they have different polarity and therefore different adherence to the stationary phase and different solubility. So the way to separate them is that they've got different polarity, tend to stick to the silica on the plate better. Okay, question 2. It does say in the specification that you're expected to be able to unpick some differences between, or recognition between some differences in physical properties of isotopes. You're given the information you need in this question to answer it. You're told that it sinks, so it must have higher density, which is not surprising because there's an extra neutron per hydrogen atom, and it does not melt when dropped into ordinary distilled water at 3 degrees. So that must mean, that second point, it must mean it's got a higher melting point, and that's B. Most of you got that. Question 3 is around successive ionization energies. This is not ionization energies across a row or down a period, across a period or down a group or anything like that. It's the successive ionization energies, the energy required to take off the first, then the second, then the third, and so on, of one element Z. And the thing to look at, if you've got successive ionization energies, you're looking for the one with a really significant gap between them. So if there's an element Z and it's got 3 electrons in its outer shell, we don't know how many shells it's got, but there's 3 in its outer shell. I know that because the energy required to take off the first, second, and third is much lower than the energy required to take it off the fourth. The fourth must be in a shell, maybe the first shell or maybe the second shell, or whatever. But the outer shell must have 3 in it, so it must be a group 3 element. Is Z3+, therefore. When it forms a compound with oxide, so the only possible thing it could be then, because oxide is 2-, has to be C. Each Z is 2+. Each oxide, each Z is 3+, each oxide is 2-. The only ratio of those that makes a neutral compound is Z2CO3, and that's the answer. Let's have a little read of the next page. Right, so question 4, you're told you've got twice the mass of neon that you've got argon. So what's going on here? So you have to work out, well, ideally you'd work out probably the number of moles of each one, which would probably be the best way to do it. So work out the number of moles by doing 60 divided by 20 for neon, which is N is equal to 3 moles, and argon is 30 divided by 40, which is 0.75, and that ratio then is 1 to 4. So if you times that by 4 and times that by 4, you get 3. That's what I'm saying there. So it's a 1 to 4 ratio. The way that I actually did it when I first thought about it was that I know that neon's atomic mass, which is 20, is half that of argon. So if you have the same mass, you'd have twice as many. You've got 2 times the mass and twice as many for the same mass, so 4 times as many. It's another way of looking at it. It's the approach I took originally. So the answer there is A. It's a 1 to 4 ratio, so 0.25. Okay. Question 5 looks kind of complex when you first look at it, but it's not too bad. We just got to take each thing at a time. You should know that if you go from 300 Kelvin to 450 Kelvin, well, you should know that the temperature is proportional to pressure. So if you increase the temperature, the pressure would increase by the same ratio. So we're timesing by 1.5, and so that would cause the pressure to go up by 1.5. So this change would cause the pressure to go from 40 to 60 kilopascals. But we're told we've lost 1/4 of the molecules, and so 3/4 then of 60 is 45, and that's the answer. Hydrogen carbonate ions, you're expected to know that the hydrogen carbonate ion is HCO3 minus. Okay, if you forget that one, you know that carbonate is 2 minus, and you just add a hydrogen ion to it, you get HCO3 minus. Anyway, it's not helpful maybe. And you should know that magnesium is a 2+ ion, and so there must be a 2-to-1 ratio, so that's B. Magnesium, one of those and 2 of those. And then the last one, I think it's quite tricky. People always struggle a little bit with the idea of resonance and delocalized electrons and so on. But you should know that around the surface, let's go through all of these in turn, around the surface of what do you call this stuff? Buckminster fullerene, you've got delocalized electrons. You should know that there are resonance forms of ozone. But this one here, so if you need to look that up, do so. I'm not going to do that now because it's not the right answer, because ethanoic acid does not have resonance forms. Whereas these ions here, and graphite, of course, you know from GCSE. But let me just draw the carboxylate ion out. So that one, it's got a resonance form that looks like that. And NO2, for some reason I always struggle to draw NO2 minus, is that, and that's got a resonance form of that. So you can flip between those two. So these electrons in that system are delocalized. That's not true for these substances, not true for these substances, or some of these substances, right? So I'm going to move on. Make sure you draw those things and know the ones that you're familiar with or that you've seen plenty of that have resonance structures, right? I have to go through that in a bit more detail if you need me to. What's the molecular geometry of SF4Cl2? And there are simply, I've probably drawn this wrong, but it's octahedron anyway. I would have thought the 2 chlorines go, oh look what I've made a mess of this. You've got 6 ligands around a central atom. It's octahedral, always the case. So that's the answer there. What is the preferred Lewis structure of nitrous oxide N2O as deduced by formal charges? We had quite a similar question to this in the mock, if I remember, the first mock, if I remember rightly. So remember that formal charges is the charge that an atom in a molecule would have if we assume that the electrons in a covalent bond are equally shared between the atoms they're bonded to, right? What that ends up meaning is if nitrogen is making 4 bonds, it can normally make 3, it's got a plus. If it's making 2 bonds, but it would normally make a 3, it's 1 minus. Oxygen's making 2 bonds there as normal, so it's 0. That's got 4 bonds. That's got 1 bond. So it's making fewer bonds than normal, so it's a minus. That's 0. Plus, unusually, this one's 2 minus. Plus there as well, because it's making 3 bonds, but it normally makes 2. Oxygen here 2 plus, and each of the nitrogens 1 minus. Now, in general, it says in the textbook, the preferred Lewis structure is the one with the formal charges are closest to 0. So that's either A or B, but only one of those is the right answer, and it's the one where the charge is on the more, so the negative charge is on the more electronegative element, and oxygen is more electronegative than nitrogen, so B is the right answer. Probably worth practicing a few of those if you can. Which pair of statements is correct? So the thing to do, just draw them on. Oxygen's always got 2 lone pairs. Nitrogen's also got 1 lone pair unless they're in some sort of funky structure like above here. So number of non-bonding 1, 2, 3, 4, 5. Is that or that? And then the number of pi electrons. Well, we know hopefully that benzene's got 6 pi electrons, so 2, 4, 6, and there's a pair of pi electrons in the double bond there, so it must be 8. 2, 4, 6, 8. D is the right answer. And then 11. What is the explanation for malleability of metals? So what we normally say, the way we normally mark this is by saying that metals can bend and be moved around. Atoms can slide over each other without the bonds breaking. The bonds are strong though, which is doesn't mean that they won't break. The bonds involve free electrons, and I can understand why people would have given that as an answer. But the answer is given as D here, and it's because that if you bend a piece of metal, the atoms can slide past each other without the bonds breaking, and that's because the atoms are bonded to all atoms in all directions. So the non-directional bonding there is the main reason. Okay, and that comes about because they've got free electrons, but the D is the preferred answer. Question 12. Here is a repeat unit of a polymer, sanodes and plastics. We've only done this fairly recently, but hopefully you can see GCSE stuff. This is the monomer. So always it's got to be a double bond in there somewhere. And I lost track of where I got to because I got distracted there. But anyway, this is the answer, A. This carbon is this carbon with 2 hydrogens coming off it. This carbon is this carbon with 2 CH3s coming off it. That's all I'm going to say there. If you need help with that, give us a shout. 13. Why is copper sulfate blue? Well, this is something you've really got to practice. Based on the paper 2, you need to practice your explanation for why transition metal compounds are coloured, transition metal ions are coloured. Right, so I'm going to go through that in quite a lot of detail in paper 2, but A is the answer there. Yeah, I'm not going to go through it all again now. Which molecule has a carbonyl functional group? So my advice here would be to draw the molecules out. So this is an ether, this is propanone, and propanone is a ketone, and ketones have carbonyls. If you're not sure, draw them out. This is a hydroxyl that you find in alcohols, and this is an amine. Hopefully no one went for that one. The block structure of the periodic table groups elements according to which characteristic? Now originally they were ordered by atomic weight, and then that eventually became that they're ordered by atomic number. So some people went for A. And if you look at the periodic table, it matches up with the electronic configuration beautifully. That's how it's designed now. Originally, atomic weight and reactivity would have kind of combined together. So I can understand why people gave D as an answer as well. But really, it's electronic configuration, hence the 2, 2, 6, 2, 6, 2, 10, just like in the electronic configuration work that we've done. Moving on. Question 16. Which element has the highest number of different oxidation states? I've been having a little think about this because I don't think this is something that's required knowledge. It's something that I remember being taught either at A-level or degree, but I don't think it's really part of the syllabus. I think this is a bit of a funky question. Now you could work out, I think, that manganese forms more oxidation states than titanium, because if you look at their electronic configurations, 1s2 all the way up to 4s2, then 3d2 and 3d5. So to form ions, titanium could theoretically at least lose its 4s electrons, which it would do first to form theoretically at least titanium 1+, 2+, and then these 2 electrons in the 3d subshell to make 3+, and then 4+. So in theory it could at least form 4 ions, and not all of them are stable, but it could form them. Whereas manganese could form 7, so losing its 2 4s electrons and then its 5 3d electrons. So the argument then, you could argue, would follow on then that copper and zinc would make even more, because it could even form like this isn't the electronic configuration, it's 4s1 3d10, remember, for copper. But anyway, and that's kind of important, I think. But it just turns out that the peak number of oxidation numbers that can be formed is manganese. Everything to the right and left of manganese forms fewer oxidation states, and I haven't really got a satisfactory answer for you, and that kind of sucks, but I'll do my best to come up with something stronger than that. What do greenhouse? I realise I'm just blowing past that question, but leave it with me. It is something to do with stability of the D subshell. I'll come back to you on that one. What do greenhouse gases have in common? Question 17. They absorb infrared radiation. We all know that. Not all greenhouse gases are emitted by burning fossil fuels. Some are, of course. Carbon dioxide can be, but it's not the only place that greenhouse gases come from. There's lots of greenhouse gases like methane isn't released by burning fossil fuels. They don't absorb UV, and you should know that they absorb infrared radiation by changing polarity when they get excited, when they're absorbed by infrared radiation. So they can be symmetrical molecules with no polar bonds, but they don't have to be. Cyclohexane. If you draw out cyclohexane, you'll see that all of the hydrogens are equivalent to one single peak, and because they're I know we have only just started doing NMR, but because they're all equivalent, the hydrogens don't couple to each other, so there's no splitting pattern. So if you didn't get 18, it's not the end of the world. We've not finished this topic yet, but there's one equivalent hydrogen all the way around, 12 of them. Butanal, so I'd have expected you to sort of tot up the butanal to start with, so it's CH3, CH2, CH2CHO. I've just totted up. The formula mass of butanal is 72, so the M plus peak is going to be 72, and that's that peak there. Little tiny peaks either side of it, don't worry about those. What they come from, this peak here to the right, is any isotopes of, any carbon 13s that are kind of in there. So 1% of all carbon is carbon 13, so you're going to see a little bit of extra mass in there, here and there. You've also got a fragmentation peak of -15, and that would be the CH3 from the end falling off, by the way. The M over Z, the M plus peak should be the same as numerically the same as the MR, which is 72. Question 20 is around the calorimetry in a cup experiment. What's the correct interpretation of this reaction? So this is an exothermic profile, which means hopefully, that the temperature goes up. Well, it's just basic knowledge. I'm just going to move on. Question 21, a little bit more working out on this one. So I'm just going to make a couple of notes and I'll pause the video. So the way to tackle these is to look at how these reactions given match up with the equation you've got to work out. That's one you've got to work out. So in the one we're going to work out, carbon dioxide is turning into carbon monoxide and hydrogen is turning into water, gaseous water, steam. Right, in this top reaction, which we're going to call A, carbon dioxide is being formed from carbon monoxide, and there's twice the number of moles of carbon dioxide. So if we turn this reaction on its head, I wouldn't write this out in an exam if I'm honest, but turn it on its head and then write it out in half the quantities, you'll see hopefully what I'm doing. So 2 lots of CO2, I'm going to make it 1 lot of CO2 going plus half a mole of O2 plus CO. So all of those, half those quantities, and reversed it. And if you do that, that comes to half that value and reverse, which is plus 283 kilojoules per mole. The second one is going in the forward direction, but half the quantities given. So we've got H2 plus half a mole of O2 goes to 1 mole of H2O liquid, and half that value goes to minus 286. And then the last one, this is liquid water. We've got to form gaseous water from liquid water. So I've got to flip this around. H2O liquid It's the H2O gas, and that's plus 44, right? If you can check that you've got this right, because if I cancel out the things on the left and right, that's on the right, cancel out with the left, that's on the left, cancel out with the right, and you're left with the equation as given at the top there. Add these numbers together, they come to 41, hopefully. So you're looking to see where these substances match up with your equation and the quantities, okay? 22, which is a renewable energy source? Wood, because you can regrow it. The biofuels question on paper 2, by the way. Loads of you think that biofuels don't release carbon dioxide when you burn them, but they're wood and they're oil that's been made from plants. They renewable energy sources, or carbon neutral ones, take in carbon dioxide when they're growing, and they release carbon dioxide when they're burning, because it's carbon neutral overall. Anyway, 23 is question B. Which are endothermic processes when forming an ionic compound? Well, we've done lots of this stuff, and actually this question was answered pretty well. So it's B, 1 and 3. So the energy required to turn or to produce 1 mole of atoms from elements does require energy, and the first ionization energy requires energy. To remove a mole of electrons from a mole of gaseous atoms requires energy. First electron affinity is always exothermic. You're adding an electron to a neutral atom that typically releases energy. Question 24, slightly harder. I'm going to stop the video at this point and use this as part 1. I'm going to finish off this paper later on, and you'll have part 2 to look at then.